We're going to talk about probability, a little bit of random variables, which are neither. That's like an actuary joke, so feel free to laugh. Some things like normal versus average, which is, and the appearance of random chance, and those two are pretty related. So, I'm Sam. I have a little game company called Wild True Fork. I was an actuary once, so I don't particularly recommend it. And I work with hospitals during my day job doing IT stuff that doesn't make any sense unless you already know what it is. Here is our agenda. We're going to talk about some basic terminology, what I'm calling dice distribution, so like Dungeons and discrete probability, some calculus stuff, specific distributions examples and how to come up with your own generator functions, and then some sort of philosophical discussion of random versus fair. So, very basic level, what's a distribution? I really want to avoid cramming a semester of probability into 30 seconds, but here it is. Probability is a value that is the likelihood of an event happening. It is between 0 and 1. It cannot be less than 0. Doesn't matter how fancy or how unlikely it is. Cannot be greater than 1, even if it has already happened. So between 0 and 1. And distribution is a breakout of probabilities for a series of events. So we have here a distribution. So this is a bar chart distribution where we have a discrete probability. So we have 6 values along the bottom here. Each one has a certain percentage chance of happening. This is the kind of thing where you could have very bizarrely shaped die, or more likely a random variable and then a switch case that you piece down to try and see which of these buckets it fell into. This is a legitimate distribution though. It adds up to 100%. That's important. Everything has a value. And then as you can see here sort of intuitively, the things that have higher values are more likely. One thing you'll notice, and this is going to become important later, is that the height of the bars and the probability of the things corresponds directly to the volume or the area the bars represent. So the amount of yellow here, like the chance of 0 happening is this amount of yellow over the entire amount of yellow in the chart. It is that piece of the event space. Continuous distributions are pretty similar. We're going to use lines to look at them mostly. And when you have to calculate the probability of an event on a continuous spectrum, things get a little bit tricky. Sort of like throwing a dart at a dartboard, the probability in a perfect world that you hit a given point is always 0. Everything in continuous land has a 0 weight. Only in the aggregate do we see things. So in continuous probability distributions, we're going to be looking at the area under a curve from a region, which you can get using calculus, but we are going to mostly get using simulation. In this case, a probability distribution has to have a total area across its range of 1. It needs to add up to 1. If it doesn't add up to 1, you're going to have some problems, and a lot of the math is going to break. And it won't be a distribution. It has to add up to 1. So here we have from 0 to 1, going from 0 to 2 here. This is a little counterintuitive, because the last example we saw, the most probability anything could have was 1. And here we have probability that the value of the density function is well above 1. And it, in fact, can get infinitely high. But the area under the curve is what matters. And since this is a triangle, the area is going to be half the base times the height, so it adds up to 1. Cumulative distribution functions are just the sums from the bottom of a range up to a given value. So if we're looking at this guy here, the cumulative function is going to be the area under this curve from 0 to whatever value I happen to be looking at. So it's going to be a monotonically increasing function, so it never goes down. At negative infinity rather, the cumulative distribution function has to be 0, and at infinity it has to be 1. It can do a lot of stuff in between. That stuff is going to be increasing at different rates. And if you want to get the chance of an outcome happening between 2 points A and B, you just get the difference between those on the CDF. And that's why they're useful. We'll talk about them a bit more later. Mean versus mode. This is actually kind of important. So mean is the average. That's the fancy name for average. It is the expected value is the technical term. And it's going to be the sum of all likelihoods, or all outcomes, weighted by their likelihoods. So for example, if you want to get the average, the mean of a die roll, let's say a d4 for the sake of making the example expedient, we would do 1 times 1/4 plus 2 times 1/4 plus 3 times 1/4 plus 4 times, that's a times sign, 1/4. And you can add that up together and you get 2.5. So that's the expected value. The mode is the most common value. So a lot of people learned mean, mode, and standard deviation back when they were in high school or junior high or whatever, or median was the other one they learned. Mode was sort of the joke at the time, I think. It has no real value, just the highest point. It's sort of a fluke. But in real life, modes are actually really important. So if mean is average, mode is typical. Mode is normal. So here, 1, 2, 3, and 4, they are each the most likely. They have tied probabilities at 1/4. So they are all the mode. If we go back to the previous continuous example, the mode here is 1, because this is the highest density. It is the single most likely one outcome, even though in a continuous distribution, you could never actually land on it, because the area under that point is still 0. So mean and mode is kind of tricky, and it's really important to bear in mind when you're thinking about this stuff, because humans use these kind of interchangeably and don't mean to. So for example, the average number of arms on a human being is slightly less than 2, because there are some human beings who have fewer than 2 and very, very few who have more. But the normal number of arms is 2. So we have a difference there. And that's something people will use, and they won't realize that this is something to bear in mind, basically. Similarly, and more relevant, the average position of the points on a circle, so the periphery of a circle, is going to be the center of the circle, even though no point in that set is anywhere near the circle itself. So the average can be something that is not only atypical, but it can be something that's actually outlawed by the restrictions of a set. And that's something just to bear in mind, especially if you're doing things that have sort of a symmetric distribution about the central axis. You're going to have a lot of averages which are 0, where a typical value might be hundreds of thousands. So the 0 is sort of meaningless in that case. And in those situations, we start caring more about nodes. So just remember that average is not the same thing as normal. And there are people who think they are the same. And so someone can say, hey, I put together this dice roll for a game I'm working on, or this thing. I like it because on average, you win 75% of the time. Or on average, you get like a 75, say. And you might say, well, okay, on average, you're getting that. But that's because you were getting 100 3 times and a 0 the 4th time, when you look at the actual numbers. So that is something to bear in mind. Median is also kind of a joke. It's sort of in popular statistics. It is the 50% mark, which means virtually nothing. It is another thing which people confuse with average. So there's that joke where it's, I don't know how many percentage of Americans, like 60 or 70, think they're above average drivers. But that's perfectly okay, as long as there are some terrible drivers. Like, as long as there are more terrible, the terribleness of these drivers is abhorrent, most people will be better than average drivers, because that average will skew things downwards. Here it's useful as a conceptual reminder that all of the distributions we look at, any probability is going to boil down eventually to a % chance of something happening. When we're talking about success checks or anything like that, or whether or not something happens, things like actual severity distributions are a bit different. But the things you want to consider are when you're building an event, when you're putting together a sort of a skill challenge, or trying to decide how likely it is that a weapon lands a blow, or what a character's chance to dodge is, think about the median, the 50% mark, but also think about the 10%, 80%, and 90% marks. So there's going to be, what are 10% of the people going to want to do, right? Those are like the hardcore people. They're going to go get every single different kind of pebble you can pick up because it goes in your inventory, right? The completionists and the speed runners and so on. 50% people, that's like your average gamer. Then we have like something where 85% of the people, 80% of the people are going to be able to succeed, that's your casual gamer. And then if something is like something that 90% of the people are going to be able to do, 95%, that's your like, I have played Angry Birds once gamer. And you want to sort of figure, as you're putting together any kind of challenge event, any kind of dodge, any kind of thing like that, think to yourself, what percentage of the time is this going to happen, and which gamers, which audience people is that going to appeal to?
So I'm curious, did those numbers come out of something, or are they just feels about
Those numbers came out of my head.
Okay.
But I will stand by them to my dying breath. Distributions is the super punny name I came up with because I'm super, super clever. So die rolls have what is called a discrete uniform distribution. It's really exciting. It is flat looking. And this is probably where the biggest source of probability fallacy comes from, which is that when most people hear the word random, they think the word fair, because dice are fair, generally. This is what it looks like if we have a six-sided die. The average chance of each number coming up is about a sixth. It's not going to be exactly a sixth because every die is going to have its own weird weights, and realistically you can never figure out what those are because the actual weights are going to be well within margin of error of a sixth. But this is the basic distribution. Now a lot of people have played Monopoly here. Yes, Monopoly, ever? Everyone knows what the most common die roll Monopoly is, right? Anyone? 7 comes up 1/6 of the time. Because when you add two uniform distributions, you actually get this. It's called a triangular distribution. Some people call it a rainbow distribution. Some people call it a pyramid distribution. If there's a thing that goes up and then down, especially if it has a point, someone named this distribution after that. Because this is one of the oldest pieces of probability there are. This probably predates a lot of the rest of math because games of chance go back a long, long time. And anyone who realized this would have a substantial advantage over people who did not realize that when you added two numbers together, you got something like this. Now the reason this happens is a thing called the central limit theorem, which is probably the most important physical law in the universe. It governs most of entropy. It governs the vast majority of everything, really. And it basically says that if you take any distribution, any random variables, and you start adding them together, and you look at the averages of the actual numbers you're looking at, the average of each distribution, those averages will form a normal bell curve. And so this is one step between this and a nice Gaussian bell curve is this pyramid. And we'll see this this is true in a lot of other dimensions as well as just sort of across the board too. So this is an important thing to bear in mind, that if you are working in, and we'll step out of video gaming and back to sort of tabletop gaming for a second, if you're designing a game system, if you're designing a role-playing game, if you're going to be adding dice together, you are just making a fancier, more complicated bell curve. That's all you're doing. And it's important to understand that to a certain extent, there's not a lot of difference between doing that and just rolling on a normal curve table. And more to the point, you're not going to see a huge structural difference if I do like 3d8 versus 2d10. Those are going to be relatively similar rolls. So there's two reasons to be rolling dice. When I say rolling dice here, I mean any kind of success check. This includes, a chance to pick locks in Fallout. It includes chance to hit in Dungeons & Dragons. Anything where you're looking at did something happen or not, rather than how much did it happen. You're essentially rolling a die. So we're going to look at dice roll rather than probability, like continuous probability, because the dice rolls are easier. There's two reasons you will be rolling a die in general, though. And they are success checks and degree checks. So success checks is a Boolean. It is a true or false. Did I hit? A degree check is how much does my longsword hit for? And we will look at longswords a little bit later.
I got one other type.
Yes.
Picking something at random.
Yes, that's true. There's also like the encounter chart, the encounter table, and those are those are valuable and those are useful. You tend to see them, I mean, they tend to have very simple tabular, this has this much weight, this has this much weight, and that's sort of the end of it. Because someone made a list and they are intrinsically discrete. And generally discrete distributions are pretty simple to work with. But the encounter rules do make up a good point, which is that if you do want to have, and we'll talk about this a bit later, actually I'll save it for them, but we'll come back to encounter tables. So, success check and degree. Some systems will combine these. So for example, if you are playing a superheroes-based game, you will often see that your success check is the degree of success check. It's, if you succeed this number, it's by how much you exceeded that number that if every 5 points or whatever gives you like an extra oomph. And they do that because in a superhero game you have a very wide spectrum of competency, and you need Superman to be able to take a fall the same as Batman. And one way you can do that is by saying you have a target and you'll always succeed because you're a superhero. Like you'll usually succeed at the base level at opening a door. But if you want to kick the door inward versus to manage to get it open versus shattering it to atoms, that's where being in a superhero campaign is actually going to impact that. Whereas for Dungeons and Dragons or any kind of like realistic computer game, you're going to get the door open, and that's all that really matters. So pure success checks are always, at their heart, identical to a percentile roll. The percentiles may be more precise than you can get in a D100, like 2 10-sided die, 1 for the 10s, 1 for the 1s, but they are always the same. If you're trying to play Monopoly, the chance of rolling a 12 is about 2.8%. It just is. So you could, any basic die roll, just build a little chart, draw a random number, and go if-then down the chart, or a case switch, or switch case rather, to get what the actual outcome is. The value of compounded die rolls is not the actual probability they generate, because these numbers are all fixed. The value is what happens when you add dice. So for example, has anyone here played Arkham Horror? Arkham Horror success check involves rolling a 6-sided die. A 5 or a 6 counts as success. Here, we have the number of dice you are rolling. Now, usually you're looking for 1 success. So you'll roll like a handful of dice, and it depends on how good you are, whatever you're trying to do. And if you get a 5 or 6, you succeed. And here's the chance of success as the number of dice go up. Now, you could use simple, like roll a 10-sided die, and if you get like a 9, you succeed or something. The nice thing about using these smaller die, rather than just a percentile-based die, is you have this great incremental marginal change as you add dice, where each die helps, but helps less than the one before it, and eventually you get to the point where things are almost certain to succeed. You're almost certainly going to get a success if you roll 10 dice, but there is a chance you will fail, and it will eventually happen. So the nice thing about die mechanisms is that they do give us these nice, or this particular example, gives us these nice distributions. That's the advantage of using different sizes of dice and different combinations, rather than just simply putting everything on a D100 table, is that it's really easy to make success incrementally more difficult or easier in a very organic and a sort of aesthetically pleasing kind of way. And there's a side note here. If you are curious about this kind of stuff, P is a % chance of success, and N is the number of dice you're rolling. The chance of succeeding is going to be 1 minus P quantity to the N. So since 1 minus P, and this is going to be less than 1 raised to the N, is never going to hit 0, you're never going to actually get 100% success. You always have some chance of failure. The other big category we're talking about is degree checks, and we will squeeze and counter tables in at the same time. So this is where we are looking for the extent to which something succeeds. And I'm going to compare here a falchion versus a longsword, which are 2 2nd and 3rd and I guess 4th edition D&D weapons. Longsword does 1d8, and a falchion does 2d4. And these are their damage tables, weighted by probability. So you can see it is extremely likely that a falchion will do 4, 5, or 6 damage. It is a consistent weapon. But it is less likely to roll an 8, whereas it can't roll a 1. So what we've done by stacking this distribution is we keep the same top, right? We have the same ceiling. We can't exceed an 8. Two four-sided die aren't going to add up to more than 8. We do get the perk of not getting the 1. I guess that's pretty good. Nobody likes getting a 1. So if you have a boss with 1 hit point left, you pull out the falchion because as long as you hit, you will beat it. Sorry, if he has 2 hit points left. My mistake. D&D doesn't allow you less than 1 damage. On the other hand, if you need to land the 8 to win, you want the longsword because it's not great odds. It's 12.5%, but it's better than whatever that is. I don't know. So let's say 5, 6 and change. It's probably 6 1/3. So this is true across the board. If you want chaos, use a straight roll from 1 to n. If you want some control, start stacking distributions in that same range. Just divide it in half or divide it in thirds, divide it into fourths, and add that many sets of those dice back in. You'll get about the same range, much more control. So if we go back to encounter tables, the classic D&D encounter table was a d20 roll. You would look up on the chart and see what it was, and that was the end of it. If you had made it a 2d10 roll, you would have had this triangular distribution, which would have meant that you could make certain events much more likely than other events. So if you look at a classic D&D 1 or 2 game, you're going to see like, oh, you encounter a young dragon or something. That's going to be as common as finding a merchant. Where in reality, for a given area, especially if you're looking at a computer game and you want to sort of generate, random encounters in the wasteland, you don't want everything to have an even chance of happening. And so having a sort of a stack distribution gives you much more control over the shape of how things work. Now, obviously, if you wanted to have even a higher degree of control, you could manually tweak these bars yourself. But the advantage of doing everything sort of procedurally is that if you're playing a tabletop game, you can't always roll something and check to see if it's 13.5% or less. And for even video games, it's just easier to do this. Usually, the rule of thumb is unless something really has to be accurate, you probably want to go 1 or 2 levels of approximation in, and beyond that, no one is going to see it or care. And it's just going to make things more complex, more prone to bugs. Door. So, calculus. Who likes calculus? 2.5 people. One of them was lying. Good. So continuous probability is all about calculus, which we're not going to be doing any of. Well, that's not true actually, but we weren't going to be doing it ourselves. We're going to be doing something called a Monte Carlo simulation. Monte Carlo simulations are extremely valuable for game development. We're looking at a couple use cases here, but I just want to sort of talk about them. The way it works in a Monte Carlo simulation is you find whatever you're using to generate random numbers, you run it hundreds of thousands or millions of times, and then you look at the outcomes. This is really, really valuable because you can have a chart that said, oh, here's the distribution. I'm using a normal distribution, right? You can have that, but that is a little bit abstract. You're missing what the actual outcomes are going to look like in the real life scenarios. And Monte Carlo simulation is also going to force you to test your math. So in putting this demo together, for example, I ran one of the Monte Carlo simulation programs that we're looking at later, and I saw the distribution looked really, really weird, and that was because I was missing a 3. So if I had just put the code in, something would have been failing, and I wouldn't know why, because it was an event failing to happen, and it was always possible that it was happening when I wasn't looking, or I just had bad luck. Running the Monte Carlo is really, really, really important. The program that I put together, which I'm going to be distributing after this on the internet, will basically do a very simple bucket sort. It'll run something quite a number of times, 100,000, 10 million, depends on the situation, and then drop it into buckets. And the buckets are going to be either in a one-dimensional array, so you've got like a pie chart kind of, that's a bar chart, histogram kind of a thing, or they're going to be in two-dimensional array and you'll actually see a 3D object in space. Excuse me. And you can do more in-depth analyses. You can put together standard deviation analysis and variance and get your skew and your kurtosis and various moments. But generally speaking, that's not going to be as important as looking at the numbers and seeing, does that make sense? I mean, what you want to do is, if you're like, everyone here is writing an MMO, right? Sure. You know, if you imagine 100,000 people, or 100,000 instances of play will happen for your game. So 100,000 people playing it once, or 50,000 people playing it twice, or so on. Run it 100,000 times. See what happens. Because humans are really bad at estimating probability. And it may seem like, oh, well, I'm going to make this thing happen 1 in 10,000 times. And as nice as it would be to pretend like we have a real intuitive sense of what that's going to look like when you run it 100,000 times, it's not going to be what you think. 10 is the most likely. It's going to be the mode. But it is very likely that when you have something like a 1 in a million shot, right, happening a million times, it's very likely it will not happen, which means that it's reasonably likely that after 2 million, it will still not have happened. And that's a really important thing to bear in mind. We'll talk about that later.
Is it similar to the birthday coincidence thing?
Yeah, sort of. That actually uses what's called the negative binomial distribution. All right, it might be hypergeometric. I have to go look. Now I sound like an idiot. People know what they're talking about who are listening to this on the tape. That is the birthday problem. For those who are not familiar with the birthday problem, is the question of how many people taken at random do you have to have in a room before it is more likely than not that 2 people share the same birthday? And ignoring some of the situational fallacies intrinsic in that question, because birthdays are not evenly distributed, the answer is 23, which is surprisingly low for most people. It's the same sort of deal where if you imagine, you know, how many, if you change it to cards. If I pull a card at random out of a deck and I pull another card at random, there's a 1 in 13 chance that they matched, right? But if I keep pulling cards, it's going to be pretty soon I will get another matching card from that. And that's why pairs are so common in poker. It's the same sort of thing. Every person you add to the room is both a birthday who's added to the list of birthdays we're looking for and one less piece of noise in the set of birthdays remaining. And they sort of meet in the middle at 23. So you can do that with this, although that is a kind of thing where you would actually just do the math and add a bunch of numbers together. And you know, that's not a very elegant problem. You get it like second week of your probability class and then never think about it ever again in terms of the actual solution. If you have questions about running Monte Carlo stuff, MathWorld is the Wikipedia of math. It's mathworld.wolfram.com, or possibly just MathWorld. So continuous distributions are what we're going to be talking about mostly, because the standard number generator for most of us is going to be a function that returns a number between 0 and 1. And you have integer functions that return a value between x and y, an integer value inclusive between those, but most of the time, especially in games, we're doing stuff continuously. We want something to appear randomly. It's relatively easy to say, oh, I want one of these doors to be trapped. It's more difficult to say, I need to place trees on a landscape in a way that looks interesting. So we're looking at continuous probability. They have a lot of applications. We have firing times or wait times. We have like physical distribution. So if I have like a meteor impact or something and I want to have debris fly away from it, I could use physics, or I could get a simple probability model to determine where things are going to land relative to it. Waiting times are really useful if you're running like a time management sim, like a diner sim. The wait times for how long customers are willing to wait, and also how long between customers would actually be modeled using what's called exponential distribution. And if you need to randomize position of stuff in space, or time, or anything that has any kind of dimension. So most people will call random.value. I'm using the Unity speak here. That's the generic accessor function for random, but every math library has some random number generator. Sometimes you have to seed it, but at some point it gives you a number between 0 and -1. I mean 0 and 1. And it gives you a number along what's called the continuous uniform or de Moivre distribution. This is what it looks like if you're drawing between 6 and 8. Again, the area under this curve has to be 1. And since I have a range of 2, that means the height is going to be 0.5. The height doesn't really mean a lot in a continuous distribution, not in the way it does in the discrete cases. Height here is a relative thing. This is a really, really, really important distribution. It is what 99.9% of the people in the world think of when they hear the word random. If I tell someone, hey, I have this game we're going to play, and I'm going to throw a die, and it's randomly going to come up red or green. And if it comes up red, I will give you $1. And if it comes up green, I will take $1 from you, right? If we play that, and they later learn that 19 of the sides of the die are red, and 1 side is green, they are going to feel like they were lied to, even though it was still a random process. So most people think of random as the uniform distribution, which is interesting because, as I say here, I think that good luck finding anything in real life that exhibits this distribution.
Single die roll.
A single die roll uses the discrete distribution.
Okay, right.
Aha! This one is continuous. That's the problem. Everything in continuous has to do with the real world, and real world is never that clean. So, that being said, it is incredibly valuable, and it's what we're going to be using to generate all subsequent random numbers, which is why we're going to praise it now. We are going to be building a bunch of generator functions which will give us random numbers, and the seed input is going to be a value between 0 and 1. So the idea is you get a generator function, you call random.value and feed that in, and you get a more interesting number back, a more natural seeming number. And there's a couple really easy ways to do it, which are going to give you a lot of flexibility, and there's a couple of really difficult ways for things that are really easy to describe that are actually really hard to do in real life. So for example, if we have a rectangular playing field and we want to spawn something in the middle, like we have like an arena setting, we want to spawn weapons or health packs or coins or trees or rocks or water or robots or ninjas. We want to be grouped to the center. There's a couple ways to do this. Open discussion. Someone name a way, or I will do it at you. You can manually place each one, which will work for certain situations and may actually be necessary. If you're writing a puzzle game, for example, you can't necessarily use random generation, especially if there's obstacles, because it may render certain areas inaccessible. So it may be that you want to sort of wave the mouse around and play randomly, and do a little editing to make sure that it looks random, but is also playable. So you can do that. You can get a smaller rectangle than the playing field and generate a uniform distribution of values in it, where I just say, here's my, here's my playing field, right? And I want to have rocks in the middle, or trees or whatever, like a forest, making a bolo map. So I'm going to do a random number going this way and a random number going this way. And wherever they meet, that's going to be my point. You can do that. It is going to generate a rectangular block of forest. And maybe that is okay. But it's going to look a little weird, because in real life, you very rarely come across a rectangular block of forest that is not a hedge. So the other ways you can do it, anyone else? Yes?
Well, could you create a function that would have results, that would generate results within a certain range, but the values themselves would be very different?
Right, right. So you can take the same, maybe instead of having a, instead of having a rectangle here, right? I mean, that doesn't work very well at all. Instead of having a rectangle, at the very least, we could put a circle in, because most 3D tools will give you something that generates a random value in a circle. But we can also say, okay, I'm going to pick some area here, and maybe the same as the larger area, maybe a smaller area, and run a different distribution into that. The question is, and and what the rest of the talk is sort of about is determining what a good distribution to put there is and looking at some sample ones. So, and then the weird thing about it is this picture here, where I want to have mostly trees here, right? And then more trees in the middle, and then an area of very dense trees. This distribution and the inverse, where we have a lot of dense foliage on the edge of the map, and then less foliage towards the middle, and then you have, like, you know, the one tree, right? These are not only, I mean, they are visually related and they're kind of thematically tied together, but the distributions are phenomenally different. And this one's really easy to make, and it's very tempting to go, well, I'm just going to flip this upside down, and we'll look at what that looks like. It does not look like this. So, demo time. Oh, look, I have a demo slide. So while we're here, 1 is the most common leading number in the world. You can look it up, Benford's Law. If you look at the population of every city in the world, about 30% of them are going to start with 1. And about 20, 2, and so on. 9 is about 4. This is called Benford's Law. It's admissible as evidence in court. It's used primarily for forensic accounting.
Can I just ask for clarification on
Yes.
this? Are you saying that's the most common starting digit in a sequence of numbers, or if
Numbers.
you say a number at random?
No, if you don't say it at random, it's numbers you find.
Okay.
Anything where there was at some point geometric growth involved of any kind will exhibit this value. So the number of fish in the sea, 30% chance starts with 1. And then you can do similar math for the second digit and so on.
That's really strange.
The proof's kind of tricky. It has to do with normal growth and so on. So let's look at some demos here. This is the Monte Carlo simulator I put together. It is called Random Sampler because I'm very, very creative. This is the 2-dimensional model. Right now, the distribution that I've plugged in, you can go to Unity and just sort of, you know, plug one of these in here. Let's do variable equals new, not that one, that one's bad. Uniform distribution, right? So I will plug this in, I run it, and when I hit spacebar, I get a random distribution here. Now, how many am I sampling? This is 1 million tests. So here, and this is normalizing it, so that the most likely outcome will be the very top of this, and everything else is normalized to that. So this is as probable as things get, as along the top here. As you can see, this is pretty even. I'm going to throw an extra 0 in there to sort of drive a point home. One of the points is that as you throw zeros in, it takes longer for this stuff to happen. This one is much tighter. Whereas if I take a couple zeros out, so now we're down to 100,000, which is a lot. Does anybody want to count to 100,000 right now? No? Okay. This is almost noisy, right? You really kind of have to pile the orders of magnitude onto this simulation to really get the true nature of the underlying distribution. And this also, you know, raises a valid point, which is that even with a relatively large number of samples, this is 100,000 people. This could be 100,000 concurrent users in World of Warcraft, right? We're seeing a pretty wide deviation in terms of what values they're seeing. Because the range here, the variance up top, is pretty thick. And that is because random numbers don't behave the way we want them to, which is going to be perfectly even and go in sequence. So this is the basic uniform distribution. I can stack this. So I'll put a new stacked uniform distribution in. Let's do 2 stacks, and I'm going to say true because that normalizes it. So now, all this is the stack distribution, is I'm taking that same distribution from before where I need a number generated, right? And I'm generating numbers between 0 and 1 here. right? When I need a number generated, I'm calling math.random or random.value, whatever, twice, adding them together and dividing by 2, right? I'm taking the average of random numbers, which you think would not make that much of a difference. This is the distribution we get. It is radically different. And again, it is the first stage in a glorious transition to being the normal curve. Similarly, if I put a third one in, so I'm now taking 3 random numbers, adding them together, dividing by 3 to get my random generation. This is the values that I'm getting. And to make it clear what this is here, this is the 0, this is 1, and the height here is the number of times out of 100,000 that bucket was hit, right? So the vast majority of the time, we are getting very close to the middle here, right? And only a little bit of the time is the average of 3 numbers going to be near 0, because you have to get 0 and then 0 and then 0 for that to land. If I make this even higher, make it a 6, you're going to see it narrows further. It's getting closer to the mean. And let's just make it a 20 to really drive it home here. Right? Now it gets even closer. The more you add this, the more inevitable the encroachment on the mean is. And that's because what we are doing is with every increment, every time we're stacking another uniform distribution on top of this, we are moving us closer and closer to the normal curve. And the thing about the normal curve is it goes for both directions at infinity distance. So as we get closer to it, our curve has to encompass more area. And so to fit in this, we have to squish it further. This here is absolutely what I would recommend 100% of the time if you need normal distribution. We'll talk about that in a second. Some other ones we can look at really quick. Let's do this one. I don't know what this one is. Okay. Here's a distribution where you can see it's very likely that we get close to 0, and then vanishingly small likelihoods of other things. So this is a good example if you want to have a very, let's look for a critical hit damage kind of a thing, where you have very consistent things here and then pushing outward. Realistically, you would never use this curve. It's too skewed for most game purposes. There might be something you could do. Falling damage, this might be something that was worth doing, where, you know, you look at sort of the, well, this is the long fall. Maybe you'd have to rotate the graph. That doesn't matter. Get falling damage some other way. So, this is our 1-stack distribution, 2 stacks, and 3 stacks. So again, I ran these with 10 million iterations, so they're pretty smooth. But if you used a normal distribution, you would see something very similar to this, except that it would be going out further because it's normal. So why use this instead of the normal distribution? Normal distribution is expensive. If you are going to be generating a lot of things, it is not cheap. It has a bunch of trig, it has a bunch of exponents, it has a bunch of expensive math calculations. It is also unbounded, which means that if you do it long enough, you will get stuff outside the ranges you want to deal with. And you can cap those by putting like a floor or ceiling in or clamp them, but that's going to cause buildup on the edges of your distribution because the entire tails will be rolled up into that point. So what I would recommend is this function right here. If you want a normal distribution between A and B, there it is. U is your random nut value, So if I want a normal distribution between like 5 and 6, I do 5 plus 1 times random nut value plus random nut value plus random value divided by 3. Done. It's easy, it's fast, it's very configurable. And it's the kind of thing where I think more people would do this if they knew how easy it was. Because if I want something to appear, like if I want trees to appear in a place, this makes more sense. Trees clump together, right? I would expect, looking at a typical piece of hill, like I have like a valley with a forest in the middle, I would expect to see a big clump of trees and then little bits of tree. I see mountains and then I see foothills, right? You see transitions in real life, and that's why we don't like the straight uniform, but you can do all kinds of cool stuff with it. So there is more, and we're going to look at the 3D implications of this. So go back to demo mode for a second. Open the 2D generator. So this is going to be a circular uniform distribution. I'm basically, what I'm doing here is, if you're doing one of these in 3D, by the way, you need the numbers to be much smaller because they multiply a lot faster when you have 2 dimensions involved. What I'm going to be doing is like 100,000 times, picking a point using random.InsideUnitCircle. I am finding which bucket it lives in a grid of 3,600 buckets, and incrementing the count of that bucket when it lands, and then I'm visualizing the buckets. And it takes a while to run because this computer is a lot slower than the one I built the program on.
How many iterations was this?
I don't know. We're stuck here waiting, so I'm up. Too many. So you can see this is a disk, right? With a little bit of fallout around the edges, and that's basically rounding error. Let's lower the number of iterations, shall we?
Before you stop there,
Yeah.
can you, I'm noticing like a line going across as this thing is, I don't know if it's...
Yeah,
line,
that's
but
a moire pattern. That is basically, these are a grid. I mean, they're arranged in a grid.
Yeah.
And when you look at them head on, the grid lines up. So sometimes you see the grid line up, and that's just like if you took 2 meshes and you push them together. Let me drop the number of samples down substantially. Oh, there's the problem. Okay, and then we'll do 50. Better. We can edit this part out because it's just quiet. But you can see the beat pattern sort of moving across it. It's this is why you have parallax-friendly texture anisotropic filtering in modern games. So not very exciting, this distribution. This is not what I would expect trees to look like. The ironic thing is it does look a little bit like a natural distribution of trees because of the fraying at the edges here.
Where are the red at the top of this?
There's red fog in the scene to make it clearer when things are further away.
Okay.
So you can see it is a pretty clear disk structure here with a bit of outliers. Mostly the outliers around the edge, again because of rounding errors. So this is not a great distribution for a lot of things. It's okay for some stuff. It is a perfect distribution for darts falling. No, it's not. Actually, you use normal for that because they're going to be aimed. I can't think of anything this is good for. It is random. It is relatively fast. It's a library function, and people know about it. That's why it's popular. I'm going to drop the fidelity even further so we can get this to actually run. So this will be, I'm going to pretend this makes it go faster. Now what I'm going to do is stack one of these on top of itself. Right? So you can see immediately we have the same thing we had for the basic 2-dimensional version. only it's in 3D, so now it's a cone-ish thing. Again, this is going to be really useful for a lot of situations. If you need to spawn stuff near a given point, and you want people to mostly spawn near that point, but also a bit further off, so this is great. You can spawn monsters, you can spawn wreckage near a crash site, you can spawn anything. This is a reasonable approximation for miss patterns. So if I'm aiming here, at the center, maybe this is where I'm actually hitting. A better, in quotes, approximation would probably be adding another level onto this, which is going to give us more of a 3D, sort of a normal bell. Right? So here again, I have like the normal distribution in 3D. And you can see it arises really, really easily. So here I'm shooting arrows at here. This is really, really good for any kind of targeting error. Anything where you're trying to figure offset from a target position, I would absolutely consider this. I mean, in some cases, you'll have to pick a value against this and then check to see if there's a thing there and then adjust it. You do whatever collision detection you're going to be doing. But it's fast enough that you can run this multiple times without having to worry about any real hit. And it's kind of cool to look at, right? It looks like a thing, like it looks like it has structure. The first thing was kind of rotating noise. This clearly has a structure to it. There's like obviously some kind of pattern going on, and we can see that very easily. The normal curve is a very visually pleasing pattern because we see it in a lot of nature. And similarly, if we want to populate trees in the middle of our little field here, we can switch to a stacked rectangular distribution. So now we have a rectangular edge, right, with more trees in the middle. And I can just scale, this by 100 meters and this by 50 meters, and I have my tree positions. Again, these are not the actual locations of trees. These are sorted by bucket. It is very, very unlikely. It is vanishingly unlikely that any of the random numbers actually landed in the same point, which is why if you do simulations like this, you do have to assign a bucket size, like a width you're looking at, because otherwise you'll never catch the number. Good luck doing math.random until you get the one float you're looking for.
That's because you're doing continuous
Yeah,
functions.
and then that's what I would do in general for stuff like this. Even though I'm moving discrete objects in an environment which is truthfully discrete, right? There are no continuous numbers in computers. They are discrete, finite machines. I would still do this because it's easier. And I don't know for certain, but I wouldn't be surprised if the discrete function call was actually slower. I mean, we're talking about fractions of milliseconds, but. So, this is a useful program to have. I would recommend you get this from the website when it's done, and you can tinker around with it. I wouldn't say it's very well written, but certainly you could write your own, or find. You can do it in Excel too. It's really easy. So where are we? Okay, so we have our stacked uniform circular and rectangular with additional stacking going on. So we've talked a lot about stacking the uniform distribution, which is really, really good unless you want anything else. The problem with stacking the uniform distribution is because of the central limit theorem, no matter how you stack it, you will just get more normal curves. I can take a D8, and I can add a D6, and I can add 3 D20s. I'm just getting a different shaped bell curve. That's it. I'm changing the mean and the spread and nothing else. Now, I can make it really complicated by adding any kind of conditional logic. So if you're playing Shadowrun, and when I roll like a 6, I get to re-roll that. And if I get a 6, I get to re-roll that, and so on. Then I'm going to get a different distribution, but it's going to look a lot like a normal, because those are relatively uncommon rolls. So we're going to look at a couple broad classes of these. The first one we're looking at is the exponential distribution. In the real world, this is what we use when we have to model wait time. So if we're looking at, let's say we have people coming into a shop or cars passing on the street or whatever, the number of cars or people who walk into the shop in a time period is modeled on what is called the Poisson distribution. And the time in between them is modeled here, the exponential distribution. This is the continuous version of the geometric distribution. This is saying I'm going to roll an infinite-sided die every instant, right? We're talking about like quantum Planck time here. And check to see if something happened. So you use this when there is a constant chance that something occurs, but it may never occur. I mean, it will always occur eventually, but for any amount of time, there's a chance that it will take longer than that. That's what you use this for. The generator function, which I am giving you here, is you pick p. P is going to be the chance that it's happened at time 1, after 1 second, or 1 minute, or 1 hour, or 1 mile, or 1 burger, right? Burgers are probably a bad example. I guess burgers are continuous. So that's p. P is going to be between 0 and 1. If you make p not between 0 and 1, this log is going to have words with you, especially if p is bigger than 1. U is going to be the random number generator. Whenever I use this u, I'm just saying 0 to 1 uniform. If you plug this in, log 1 minus u divided by log 1 minus p, you will get this function. Let us look at it, and I will ask the obvious question of what's wrong with the function. Is this making sense to people so far?
Yeah.
Okay, no one thinks this is a waste of a Saturday, except for me or whomever. I'm kidding. I think I called it geometric, even though it's not. Yeah, well, whatever. All right, let's pick a value. Somebody pick a value, how likely something would be. It doesn't matter, by the way. Any value between 0 and 1. Good, point 2. It doesn't matter, because all that value changes, if we look at this curve real quick, right? All that value changes is how the scale of this curve, it scales basically linearly. It's not going to appear to change, especially in this function. So here it is. Here's our curve. What is the problem we're noticing here?
It's kind of inverse of what you had a moment ago.
Oh, no. This is what we expect, right? So I'm saying here, if let's say I have, I'm saying I have a 0.3 chance of something happening in a given minute,
Well,
right?
it's outside your range, too.
Yes, that's the big problem. But what I'm saying here is, this is basically 0.3 right here, up here, about here. This is about 30%. If it doesn't, and we're saying, okay, how long does it take? Well, if it didn't happen the first minute, it's still pretty likely to happen the second minute. So, but we had to get past the first minute, which is maybe the most likely minute. So, we'll go here. And you see it sort of fades off naturally. This is an unbounded function, though. Like the normal distribution, if I switch into editor mode for a second, you can see this function goes on for quite a while. What?
I was thinking, as you continue to rotate, it's going to not like displaying that.
Yeah, it goes on for quite a ways, and indeed it does cause display problems because the draw calls. We can actually figure out how many dots there are by looking at the draw calls. It's a lot. I'm not going to. There's probably tens of thousands of these buckets because I gave it a fixed bucket width, and I said these are the size of the buckets. But the buckets live forever because, there's always a chance that the random number generator rolls 1 minus the smallest float it can. So the problem with this distribution, which is that even though it is great, is that it is unbounded. And we could say, well, if you're past this point, you're going to be here. Well, what that's going to do is mean that we have a curve that looks like this. And then it's too high to fit on the board, So the other option is to say...
Just imagine that really long tail.
Yeah.
Flipped up and kind of
essentially, yes.
pushed against the wall.
The other option is to say, well, if you're outside of this thing, roll again. The problem with that, from a computational perspective, is that that does not have a guaranteed halting state. There is a chance it will just keep rolling outside your range, and it's not very likely, but eventually it will happen and you'll be sad. So the correct solution, or the best solution here, is to only use this when it's okay to have an infinitely large wait time. And for sometimes, I mean, alternatively, you can make the wait pretty steep. If I made this like 0.95, we're going to start to see some changes. Oh man, that's a cooler ringtone than mine. It's like a 0.98. As you can see, substantially different curve here. It looks the exact same because it scales, it's normalized. But if there were values here, you'd see it was very different. So that is the geometric distribution.
And what are those in practical terms used for?
Wait times, modeling. Yeah. So typically, I mean, the catch is that these are wait times, but the wait time at a given moment, the expected wait time will change. So you have a continuously changing geometric distribution that's sort of wibbling and wobbling out of range as you go through any kind of cycles. But if you wanted stuff falling, raindrops, if you want like just a dropping noise, having a geometric distribution is going to be very natural sounding, as opposed to just, I'm going to drop every 3 seconds. I mean, it depends, actually. If you have a drip coming off of a roof, that's going to be very normal because there's a flow of stuff going into it.
Right.
If I want to have very natural sounding light rain, then just take a couple of these generators and have them sort of spit off, scheduled drop sounds, and it's going to sound really, really natural. Geometric distribution is one of the ones which is built into the world. We're used to seeing it without ever recognizing it so often that when you use it, it does sort of trigger a lot of sort of innate human reasoning. So the exponential distribution looks like this. It is an unbounded function. So be careful with it. It can sting. Other distributions that have cool names that you'll want to look at. The binomial distribution. This is really, really valuable for dice rolls. The negative binomial distribution is really, really important for calculating the number of people you'd have to have in a room for the odds of people sharing a birthday to be greater than 0.5. The hypergeometric distribution sounds cooler than it is. Gamma function. I hate it. It's really, really gross calculus. You have to do 3 or 4 layers of Poisson distribution. This runs half the waking world. This is the number of people who are going to walk into your store today. This is the number of people you are going to wave to. This is every event we see is Poisson, and that is because if you look at the events in a Poisson distribution, the difference between them is exponential because everything we see is events and then waiting for more events. Those two things are our world, with, of course, the magic of the bell curve to normalize it all. And then de Moivre is the fancy name for a continuous uniform because some guy discovered that you could have a straight line. Tools for continuous distributions. We're about to look at some really awesome, very, very high quality art that I drew. Grapher is a program that I use very commonly on my computer. It is a 3D grapher and a 2D grapher. It's a graphing calculator. It's useful for, what I've used it for a lot actually, is finding the right polynomial to use. So a lot of times I will want something to bounce in a certain way. Maybe over a range of values from 0 to 1, I want it to bounce this high. I can sort of, find the polynomial I want by multiplying the roots and then scale it up as I need to. Math World is like Wikipedia for math. It has articles and more math than you want. Wolfram Alpha is, I think, the basis for what runs Apple's Siri. I believe that's the case. You can do a lot of stuff. Not as much stuff as they would like you to think they can do. And they also want you to pay for it. But what we're doing, you can do for free. Pencil and paper is fun and a brain. Not yours. Someone else's. So, Remember I said that the normal distribution was easy to fake and that the opposite of it was hard? Let's talk about this. This is hard enough that the first slide deck I made for this was extremely broken and failed entirely. Oh, I've duplicated this slide. I'll just go to the next one then. Good, next slide. So the first thing you want to do is sort of draw this, right? And then you want to find a curve that is about what you're looking for. I'm going to call this about a parabola. Okay? Seem reasonable? Now I open Grapher, and because I'm a math major, I just do that. There's our curve. It's 4x squared minus 4x plus 1, right? So let's plug that into our generator function, right? We can look really quick. We see this goes from 0 to 1. These are the values we want, right? So we'll plug it into the generator function. You should know by the tone of voice and the exuberance I'm exhibiting, this is not going to work. What did I call it? Edge hugger. So again, we are looking for this distribution, and when we run it, this is what we get. Hooray! Not really what we're going for, right? And that is because this shape is not the actual distribution. This is the density, like the actual outcome of it. This is like the density function of it. And density, you can't just, I'm going to start this whole paragraph in my head over. This is the outcome of what we want to plug into it, right? But it's not the density. Because if you look at what we're seeing here, right, we want a lot of things near 0, right? And then a lot of things near 1. But when I look at this function, what I'm seeing is there's a lot of area here from around like 0.25 to 0.75, right? These values are all near 0. Because the height, right, is what's actually going to be splaying across the side of it. This axis is akin to this axis. And in fact, you will find that if you do some fancy math, we'll skip to the next slide. So it doesn't work. And this is actually how we're going to do these in general. You find the cumulative distribution function, which is calculus. You invert it, and then you plug random value into that. And you may have to tweak a little. It's going to depend a lot on what you're doing. And especially if once you've done these things, you end up with roots. Generally speaking, even though you or I may look at -1 and go, oh yes, you can take a cube root of that, it's -1. The computer is going to go, this is a negative number and I'm having none of it. It's going to give you a nan and not error out because it's trying to be helpful and you're not going to know why half your distribution is missing. Okay, so Wolfram alpha. It's hard to read a little here, but basically I went into it and I wrote integrate 4x squared minus 4x plus 1. And it just gives me a function which is here. Now it's hard to see here, but remember the most important thing about a density function, or sorry, a cumulative distribution function from slide 3, right? It has to start at 0, has to end at 1 over the range we care about. Starts at 0, that's great, right? But over at 1, it's like 0.333333. It's a third. So we actually have to multiply this whole thing by a third in order to scale it up because probability works in one space and not 1/3 space. So I multiply the whole thing by 3. And then here I say invert 3 times the function it gave me before. Now you could write integrate your initial function, but if you need to scale it up, you're not going to know that at that stage. So it gives me this formula here, 1 half times 1 minus the cube root of 1 minus 2x. Now, if you do this, numbers that are greater than 0.5 are going to error out, at least in C#. Even though negative numbers have legitimate cube roots, it's just not designed to see them. So I took care of that, and you can look at the code and see, but basically I just check and see if this should end up being negative, save that, and then put the absolute value into the root, and it works fine. This is the curve that gives us, which is much more what we wanted, right? And it's not super difficult, especially because most curves you're going to want are going to be this curve or one of the curves we've already looked at. And you know how to do this one now. And the function in here, this 1/2 times 1 minus cube root 1 minus 2x, that's going to work for any inverted parabola distribution you want. And if you want it to be, I mean, you can be fancy and start adding it to itself. We can do that if you want to see what it looks like. I have no idea, but it's going to start approximating normal. So it'll probably be, it won't hit 0. It'll be more in the middle. Okay, so caveats. You will be taking lots of roots using this, especially because if you have lines or quadratics, when you integrate them, you're going to get cubes or squares, and when you invert them, you will get roots. Computationally, square roots are a little slow. I mean, that really only matters if you're doing a lot of stuff, but just bear in mind that if you're trying to run like 100 million iteration-wide Monte Carlo simulation, that you're going to feel that a little bit. It'll be seconds at least. You can count it. I already mentioned this. You have to worry about negative numbers with roots. And it's pretty straightforward. Just feed an absolute value in and then invert the answer when you need to. You have to sort of use human judgment. If it is a square root, you really shouldn't be having negative numbers there, and that might be an indication you have a problem. If it is a odd numbered root, negative numbers are fine. Thanks, complex analysis. Cheating. So it's cool to be super precise and mathy and integrate and invert, because it is kind of cool that you can go to a website and it will do your homework for you, or your homework from 15 years ago. I think you can actually get it to show work too, if you have Pro. That's how they get you. But you don't always have to do that. So here's a simple distribution here, right? I just want to have most, and again, what we look at here is this number here is the value, and this is the probability. So most things are going to be in the first, half, and then a smaller amount away from it. We can use that instead of a geometric distribution. We have that sort of fancy curve. This is going to get the job done, and it's bounded. So it's not going to go off forever. And if you do that, you'll end up with, using the previous algorithm, this is the generator function you'll get, which is cool, I guess. But you might as well just use a straight line, because it's almost a straight line already. So, I mean, just the important thing is to, when you're doing these situations, don't make things too complicated. No player is going to be auditing your code. And as long as you don't use like the basic uniform distribution, you're already more, in quotes, realistic than anything else that's happening. So randomness and fairness, this is sort of the last topic. It's a bit fuzzy because it's very, very, very site-specific. But when we talked about this a little bit before, most people confuse and conflate random and fair. When I say pick a number at random, they think two things. They think that it should be from the straight normal distribution. Like when I say normal, I mean like uniform, right? Distribution, and they think that the outcomes of those will be nice and smooth. So there's a classic experiment, which we can do if you want after we're done here. Basically, this is like day one of like every intro probability course. The teacher says, professor, I guess, because the probability course says, okay, here's the deal, 2 teams. Your team has pennies, your team has pencils. You are going to flip this coin 100 times, write down on the board H or T in sequence. Other team, just make up a sequence, write it on the board. Teacher leaves, they do this without the teacher being there, right? Professor comes back. It is painfully obvious to people who know what to look for which sequence is fake and which one is real. Humans think random looks like heads, tails, heads, heads, tails. See, a little variation there. Heads, tails, 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 heads, tails, heads, heads, tails, tails, and so on. And in 100 flips, you're going to see like a couple strings of 5 and maybe a string of 6 or 2. And humans aren't going to put those in because they think it looks unnatural. Humans are bad at randomness. So one thing to bear in mind, right, and this is sort of the Machiavellian game designer talking here, it is more important that your game appears to be random in the appropriate ways than that it is random in the appropriate ways. If you think, oh, in real life, this would be a normal distribution here, and players are like, everything's just spawning in the middle, and you're like, well, okay, but they would be falling, and, on average, they would, if that's a problem, spread it out. Drop down to a pyramidal distribution or a cone distribution, or drop down to uniform, right? Appearance of randomness and the appearance of fairness is more important than actually being accurate because these are games, not simulations. What humans do like is quasi-randomness. Quasi-random is a kind of a fuzzy concept. It has a technical definition, but we're going to sort of skip to the sort of layperson version. But essentially, most random number generators have what is called no memory. Like, you are never due for that head to come up. I mean, I don't care if you got like 1,000 tails. You're not due for heads any more than you were the first time. This is why gambling is addictive, because the human mind is like, any minute now, I'm going to work this out, right? I am due. And to a certain extent you are, because slot machines are regulated by the government to have a certain level of payout, but not the kind of payout level that is going to mean you are due. The only times you are due is, I believe, the New Jersey State Lottery requires that it has a running average payout of a certain amount, and periodically they have to compensate for that. They've had a bad run of no one winning, so there'll be a month where the average payout of the lotto is like 104% of what you put in. And what happens is that like hedge fund managers from New York flock down and buy hundreds and millions of dollars of like internet-based like tickets just for the like immediate 4% return. So anyway, that was sort of irrelevant. It's just kind of cool that that happens, I guess, and that we can't take advantage of it because the problem with arbitrage is you need a lot of money for it to work. But quasi-random generators are things that have memory. So they say, oh, okay, here's a good example, right? Who's ever looked at a night sky? Yes. There are these little points of light, which are actually giant balls of gas many, many kilometers away. And you'll notice that they form shapes. Or at least people a long time ago noticed that, which we call constellations. And the reason we call them that is because they're close together. But if you ask a person to draw a night sky, they're going to go like this. And it's going to look like a bunch of dots evenly spaced, like an ideal gas, across the piece of paper. Because humans don't like doing this and then that. Because that looks weird. I had to have the intention of go putting it near that, but it's random. They shouldn't be close together. When the reality is you expect clumping. So quasi-random functions are generators that will actually make sure that we don't get clumping. Or that we reduce clumping. So an example of this is if you have a game where a series of obstacles comes at the player, or they get a series of power-ups. So Mario Kart is a good example. To a certain extent, if you're writing a game like Mario Kart and you have power-ups, maybe you don't want to make it very likely or possible that a player gets the single banana every time in a game, because that's frustrating, right? So there's a couple of ways to handle that. One, for that particular example, spawning discrete instances, obstacles, enemies, power-ups, sound effects. This is a really good one for that. It takes people out of the game if they have a sound effect, the same sound effect twice in a row, for something that's sort of loud and noticeable. So if you have like 3 or 4 sound effects for something, pick one at random, but maybe if the one you pick is the one you just picked, pick a different one. Or, what I tend to do in things like this is I'll keep track of the last 2 or 3 things, and maybe a list of 20, right? And I'll say, okay, I just spawned one of these obstacles. I'm going to roll again. I'll take whatever it comes up with. So I get the obstacle again, fine. But it makes it much less likely that I'm going to have streaks while still allowing for some clumping. Because clumping is natural, although human beings hate it. This is a really, really easy system to use. You just need an array of the pointers or whatever to whatever you're picking from. Check against it, reroll, simple. The other common issue for sort of tweaking rolls is for rare events. It's sort of like a black swan situation. People are really, really, really bad at determining how often rare things are going to happen. So the example here is in an MMO. If you have like your rare drops, you got like the pirate hat that 1 in 1 million dinosaurs have, and it's got like a pirate skull, like a dinosaur pirate skull. Like it's super badass for your like goblin rogue to wear. You can tell that I know a lot about World of Warcraft because I know words they stole from Tolkien. And so maybe you say it drops 1 in a million or 1 in 10 million from this guy because it's really, really rare, right? You want it to be prestigious. The problem is it cannot be prestigious if no one knows it exists. So what you will see them do for things like this is when they introduce, and I'm sure Valve does this too for their, I think they have more hats in Team Fortress than there are atoms in the universe now. When they introduce a new thing, you crank up the odds for a little bit. And it's either for a time period or for a certain number of things being added. So for example, you could say, I'm going to have a minimum active seed population. Let's say I have 100,000 players in my game, and I want at least 30 to have this awesome hat so that people know it's there, and they can drive the economy and so on or whatever. So what I might do is I might say on the server, every day someone doesn't get one of these hats until I have 30, until I have my seed population. Every day no one gets one, just crank the odds up of someone getting it by 25%. So eventually it'll become relatively likely that someone's going to get it. And people will get the hats, people will know about the hats now, and then it will normalize back down to the rate that I set, that my economists set for me. And the nice thing about this is if you do it gradually like that, people who are really early in farming and from a strictly exploitative, whichever one of those is the correct form, perspective, the people who are giving you the money in the game, you can reward them because they're still more likely to get the hat. This only works for hats. Here's some cool math. If you have a probability of event happening, so this is a success check, and the probability is p, and we're going to try n times, the chance of it happening, we've already looked at this, is 1 minus p to the n. But the interesting thing here is that if I take something that has a 1 in 100 million chance of happening, and I do that event 100 million times, there's like a 36% chance it doesn't happen. And it actually approaches 1 over e, because math loves throwing e in just randomly, especially when exponents are involved, or when they're not. So the thing to bear in mind here is that, do not in your head go, well, if there's a 1 in a million chance and it's happening a million times, it is going to happen at least once, because it is going to happen on average once, and it may happen nonce. On the other hand, if I have a 1 in 100,000 event, and I run it a million times, the chance of at least one success is like 99.995. It's actually 99542, I think. which is much more likely. Now, to a certain extent, I mean, per the previous slide, if you have an event in your game, you should make sure that the chance of it happening somewhere is 1. It should happen. Otherwise, why did you do it? Right? That is, you could have just said, oh yeah, it's a door. I'm just not going to put a room behind it, instead of putting a room full of treasure that no one will ever see. Because you had to pay someone to make the treasure, and to code the door, and to furnish the room. That's more or less it. So if there's examples, you want to work through stuff, I think we've sort of covered all the obvious ones that I could think of. I'm going to release these slides as a PDF, although I'm going to remove the extra slide. I will put the random generator Monte Carlo simulation up, so you can feel free to tinker around with it. Definitely feel free to email me if you have a question about how to get a specific function, or something isn't working, or if it keeps asking for your credit card number more than once. I'm kidding, I won't do that at all. Anything else? Questions? Come on. It's like ask an actuary. Yes.
Something I think about with like kind of cutting off a geometric distribution where the chance of there's something happening, and then where, you know, if there's X% chance, how many times will people have to do it before they get a success?
Yeah.
And you don't want people to be able to have to do it 100,000 times before
Right.
they get a success.
You actually want to use, oh man, I really wish I think the negative binomial is what you want. There's a distribution you can check, which will give you the odds of, and we can do it right now actually, the odds of, for a success-based check, how many times you have to go before a success. And the way it works, really, really briefly, is in probability, P and Q are enemies. Good? Okay. So probability is success, and Q is 1 minus P, right? So if we have an event like this, the probability of it taking 3 tries before you succeed, so you succeed on the 4th try, is going to be Q to the 3 times P. And therefore, the odds of succeeding in the first 3 tries are going to be P plus QP plus Q squared P. And the nice thing about this is that because this is going to be P plus 1 plus Q squared, dot, 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 and Q is less than 1, this is a converging geometric series here. And you can actually, there's a closed form you can get with this on Math World to solve it explicitly. There's a similar thing you can do. It's a little bit more complicated if you're looking for how many trials before 3 successes or 4 successes. That's a little trickier because it's not just, you know, I can't just do fail, 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 succeed. It could be fail, succeed, or fail, fail, succeed, succeed, or succeed, fail. I'm not going to go through all the iterations. But this is the sort of general form for that. And this is absolutely something you want to consider. Even if you don't have explicit things going on, if you have a series of skill checks, think to yourself, what are the odds of someone succeeding at this? Is this like a 85% thing? Is it like, okay, this guy doesn't know how to jump, he jumps like this, right? Or is it like, ever hear play Cave Story? Cave Story is a great game. Everyone should play it. There is one jump in the game. It is the most important jump in the game, and for that reason, it is a great idea that they made it optional. If you fail to make the jump, the story goes the regular way. If you succeed, you have entered hard mode, which is quite difficult. But it is a difficult jump. It is a platform where you have like 3 pixels of leeway to make this jump. And you only get 1 shot, and the save point's a long way away. If you have stuff like that, try it, give it to a couple people, see what percentage of people do it. And then if you have one right after that, do the same thing. Figure out what the odds of succeeding at each individual skill check in a level is, and multiply those together, because in a sort of approximate way, that's going to be the odds of someone just sort of nailing the level the first time through. Now, it's a little bit tricky because someone who succeeds at one skill check is more likely to succeed at other skill checks. There's a lot of covariance involved. It's very exciting. They're not independent variables. But that's something to just think about it, right? Especially if you have actual random numbers determining if an event that is important for the gameplay happens, look at it and say, how often is it that these are actually all going to happen? Or failing that at least, how often is it that at least one of these cool events is going to happen, right? Like if I have a bunch of random cool things that could happen over the course of a platformer, I'm not saying that like they should happen every time, but throw it in the first time the game's played, you know, just to pull people in. And then maybe at least once every 3 or 4 times. Something should happen if you're going to have random stuff. Otherwise, again, I mean, there's a place for having like a sanctum sanctorum in your game that only the truly elite people will ever see. And that place is you're probably not trying to make money with your game, unless you're Final Fantasy. And you're like, oh, we have a guy who's 1,000 times more difficult from the end boss, and you have to beat him in 3 turns, or he turns you into a pumpkin in real life. So yeah, basic dice rolls, QMP. Fun, easy peasy. Anything else? Cool. Well, thank everyone for showing up. Again, random numbers, they're useful. They're one of the couple tensions you can add to a game. And if nothing else, just the next time you put randomness in, consider not using a straight random call. Yay. The end.